Good morning, viewers. Now, in this video, we are going to discuss about Clausius-Clapeyron's latent heat equation, okay, which has a lot of importance and practical applications in our everyday life also, okay. Now, we have seen about Maxwell's equations, Maxwell's first equation, second, third, fourth. There are four Maxwell's equations. First equation is based on internal energy. Last equation is based on Gibbs free energy. Okay, second and third equation, there is nothing like there is no specific order of Maxwell's equations. Okay, first equation of course comes from that internal energy concept. Second one we have taken from enthalpy. Third one is from Helmholtz free energy. Fourth one is from Gibbs potential. Okay, right, H equal to U plus PV. That's how we have defined F equal to U minus TS and G equal to H minus TS. Okay, so first equation is always common in all textbooks. Okay, fourth equation also will be common in all textbooks because Gibbs free energy comes only after we define enthalpy. Okay, but this about second and third, right? In some books they'll take this as second one, this as third one, like that. Okay, there is no difference at all. There is no difference. There is no specific order for Maxwell's equations. Okay, now you take an equation which has come from the Helmholtz free energy equation, right? Dou P by dou T at constant V equal to dou S by dou V at constant T. Okay, from this Maxwell's equation, in some books you'll find it as third equation, in some books you'll find it as second equation, does not matter. Okay, now from this equation, right, what we do is, it is Clausius-Clapeyron's latent heat equation. Okay, I'll multiply and divide with the absolute temperature T, right, numerator and denominator, such that I'll write here dP by dt. Now I'll take out this constant volume, constant temperature, they are understood. Okay, T into dou S by T into dou V, I'll write. Okay, T dou S is nothing but delta Q. T dou S is nothing but delta Q by T into dou V. Dou V means change in volume. Okay, change in volume in phase change, I'll write it as Vf minus Vi. Okay, Vf minus Vi. Okay, final volume minus initial volume is change in volume. Now, this is dP by dt, change in pressure to change in temperature is equal to delta Q by T into Vf minus Vi. Now, the purpose of Schrödinger, the Clausius-Clapeyron's latent heat equation is, we apply it for first order phase changes. Clausius-Clapeyron's latent heat equation is applicable for first order phase changes only. What are first order phase changes? First order phase changes are those phase changes which require some heat for the phase change to occur. That phase change has to occur means, right, from solid to liquid phase, or we want to take the matter from liquid phase to solid vapor phase, you have to supply some additional heat. Okay, so transitions or phase changes which require some heat for the phase change to occur, right? They are known as first order phase changes. Okay, right? What are the examples of first order phase changes, right? Melting of ice means melting of any solid into liquid, and boiling of any liquid into its vapor or gaseous phase. Okay, first one is known as melting process, second one is known as boiling process. Now, you take ice for example. You take ice at minus 5 degrees Celsius and start heating it. When you are giving heat to it, its temperature gradually keeps on increasing. From minus 5, it becomes minus 4, minus 3, minus 2, minus 1. It comes to 0. You can watch it in your thermometer. Increase in temperature. You are giving some heat, its temperature keeps on increasing. But at 0 degrees Celsius, what happens is, you continue to heat it, right? You are heating it, but temperature will not rise. Okay, temperature will not rise. Till when? Till the last piece of ice also transforms into water, changes into water. Okay, once the last drop or what you call speck of ice also changes into water, then, right, if you continue to heat, then water's temperature keeps on increasing. What is happening to the heat given by me during that melting process, during that melting of ice into water? Okay, that is what you call used to convert solid into a liquid. Okay, because it is not apparently showing itself by rise in temperature, we call it as latent or hidden heat. Hidden or latent heat we call. So that is known as latent heat of fusion, or what you call latent heat of fusion of ice we call. It is 80 calories per gram. Okay, so this, what you call Clausius-Clapeyron's latent heat equation. This Clausius-Clapeyron's latent heat equation is applicable for first order phase changes which require some heat for the phase change to occur. Similarly, same is the case with water also. You will get water at 100 degrees Celsius. Okay, continue to heat it. Temperature will not increase till the last drop of water transforms into steam. Okay, temperature will not rise. What is happening to all the heat I am giving? It is in the hidden form. It is used to convert water into steam. When entire water transforms into steam, then again its temperature keeps on increasing. That's why I'll call it as latent heat of vaporization. Okay, so I'll take this delta Q, whatever is the amount of heat given for the phase change to occur, right? That I'll take it as latent heat. Now, this is known as Clausius-Clapeyron's latent heat equation, right? Here, dP by dt equal to change in pressure by change in temperature is equal to, now I'll write it as L by T into Vf minus Vi. Okay, where is Vf is the final volume after the phase change, Vi is initial volume, that is volume before the phase change. Okay, now we have seen there are two types of melting processes, and solids becoming liquids and liquids becoming gases or vapors, right? We'll apply to those. Okay, now first we'll go to boiling process. Okay, right? In boiling, what happens when you boil any liquid at its boiling point? The volume of the gas or vapor is always more than the volume of the liquid. Okay, volume of the gas, and they always occur at constant temperature and pressure, remember. Okay, first order phase changes occur at constant pressure, constant temperature. Okay, so at constant temperature of 100 degrees Celsius, water, right, boils into steam. Till throughout the boiling process, pressure remains constant, temperature also will not rise. So they are isobaric isothermal process. Isobaric isothermal process. Okay, right? The heat required is known as latent heat. That latent heat of vaporization is L here. Now, what is Vf? Vf is volume after the phase change. Okay, after the phase change means liquid is becoming gas or a vapor. Volume of steam is always more than volume of liquid, water. So in the case of boiling point, okay, now I'll apply this to, right, boiling process. For boiling process, okay, Vf is greater than Vi always. Vf is greater than Vi always. Okay, such that latent heat is positive only. Okay, temperature, capital T, absolute temperature is always positive. In the case of boiling, Vf is greater than Vi means what? This entire RHS term is positive. That is dP by dt is positive. Okay, dP by dt is positive. So dP by dt is positive means what? Okay, whenever there is change in pressure, okay, on what you call the final pressure is more than the initial pressure, okay, dt is also positive. That is, whenever you increase the pressure on the system, on that liquid, okay, it's what you call boiling point increases. Okay, whenever you decrease pressure, boiling point decreases. Okay, this without knowing we all know. Okay, and we have, after understanding this, pressure cooker has come. Okay, in a pressure cooker, what happens, right? We'll take some water in that pressure cooker, we'll close it with a lid, and one whistle will be there. Okay, when you are heating, right, water becomes steam, that you are not allowing that steam to escape. Okay, steam will be developing inside, right, building pressure on the water. So water, instead of boiling at some 80-85 degrees Celsius, normally we say boiling point of water is 100 degrees Celsius, but practically that is for a pure water at a standard pressure and all. Okay, normally, right, water in our houses, it's not 100% pure water. We'll have too many dissolved salts, so it may boil at 80-85 degrees Celsius. And so water which is boiling at 85 degrees Celsius at this normal pressure, because of the pressure of steam exerted on it, it will stop boiling. Its temperature rises, okay, to 87. Boiling point will rise to 87. At 87 it keeps on boiling again. Still more steam will come, pressure will increase more. Okay, boiling point will again increase. That is, normally in our room, if water boils at 80 degrees Celsius or 90 degrees Celsius, in a pressure cooker it boils at 90 or 100 degrees Celsius or 95 degrees Celsius, like that. Okay, so when water is at higher temperature, right, heat content is more, so whatever we put inside will get cooked faster. Okay, right, if pressure is less, boiling point will decrease. Pressure will less. Suppose a water is boiling at 70 degrees Celsius only, so up to 70 degrees Celsius temperature will rise. Cooking of whatever you put inside, potatoes or rice or whatever wheat you put, right, will start. But at 70 degrees Celsius, what is happening? Whatever heat I am giving, right, in the form of stove, that heat is not used to cook the whatever matter we are putting inside. It is used to convert water into steam. Okay, so all the heat energy you are giving will get wasted in converting water into steam. Your things, whatever you are putting inside, will not get boiled, okay, quickly. So when at reduced pressures, it takes more time for rice or anything to get cooked, right? At high pressures, things get cooked very fast, because the higher the temperature, the faster will be the cooking, okay, right? So that's why on mountain tops, on hilltops, etc., in Himalayas, etc., right, the boiling pressure will be extremely less. When pressure is very small, less, right, water boils at a lower temperature, it becomes difficult for cooking, or cooking gets delayed. Normally at sea level, right, if suppose something, potatoes, 1 kg potatoes get boiled in 30 minutes, on a hilltop, it takes 1 hour time. Okay, so as pressure increases, boiling point increases, pressure decreases, boiling point decreases, right? The concept is used in pressure cooker, where we don't allow the steam to escape from the cooker, right? It will keep on building up pressure more and more on the water. Boiling point of water keeps on increasing, okay, right? Such that instead of water boiling at 80 degrees Celsius, it takes me 20 minutes to cook something, say, because now water is at 90-95 degrees Celsius, a hotter water boiling will be faster. Okay, you can observe that when you open the pressure cooker after boiling, everything is over, lot of steam will be suddenly coming, because you have suddenly reduced the pressure from whatever built up pressure inside, you are bringing it to normal temperature. Boiling point will keep on reducing. Water will be in a superheated state there. Water should boil at 90 degrees Celsius. You are putting it at 95 degrees Celsius. So what happens? Immediately, right, water keeps on converting into steam. That we can observe once you open the mouth of the pressure cooker. Okay, that is one application of, right, Clausius-Clapeyron's latent heat equation, right, effect of pressure on boiling point. Remember, for any liquid, as pressure increases, boiling point increases, as pressure decreases, boiling point decreases. Okay, next one, we will see the effect of changes in pressure on melting point. Okay, right, for melting process, for melting process, means solids becoming liquids. Here dP by dt is equal to L by T into Vf minus Vi. L by T into Vf minus Vi. Vf is final volume. Final volume means what? When a solid, right, melts at some specific temperature into a liquid, volume of the liquid. Vi is initial volume. Initial volume means when the matter is in solid state. Means this is the volume of the solid, this is the volume of the liquid. Both will be at same temperature only. Both will be at same temperature. Now what happens is, here we get two cases. One is some solids, right, volume will increase with increasing temperature, okay, with increasing pressure, sorry, right? So when you increase pressure, their melting point increases, right? Example, that is case 1, I'll write, right, for substances which expand on melting, like wax, sulfur, okay, sulfur and metals, many metals, right? When you melt a metal, its volume increases slightly. Final volume means liquid volume. Liquid's volume is more than solid's volume, okay, right? Example is wax, sulfur and some metals. When you melt them, right, their volume will be slightly more. Okay, that is final volume is greater than initial volume. Vf minus Vi is positive. L is anyway positive. Absolute temperature is always positive. So dP by dt will be positive. dP by dt is positive implies what? dP by dt is positive implies whenever you are increasing the pressure on the system, right, its melting point increases. When you decrease the pressure on it, melting point decreases. Okay, this is for substances which expand on melting. Okay, sulfur, wax, etc. When you increase pressure on that, their melting point will increase. Okay, instead of melting at say 20 degrees Celsius, it will melt at 21 degrees Celsius. Okay, means it will be in solid phase only up to 21. Same as in the case of boiling point. Okay, right? For metals also, most of the metals, when you increase the pressure on the metal, instead of melting at some 560 degrees Celsius, it will melt at some 570 degrees Celsius, like that. Okay, now there is second case also here. This is somewhat interesting. Okay, for substances, here we have Vf greater than Vi. For substances which contract on melting. Substances which contract on melting. Some substances, best example is ice. Okay, you take a piece of ice at 0 degrees Celsius and supply heat, give that latent heat of fusion, that 80 calories per gram. Right, you measure when the entire ice gets converted into water, you measure the volume of water. Volume of water will be slightly less than the volume of ice. Okay, means what happened to ice? Ice volume has decreased when it got converted into water. Or in a refrigerator, you keep on cooling down. In a deep refrigerator, right, you keep on cooling water till 0 degrees Celsius. You take out that latent heat of fusion, right? Water will transform into ice. When water becomes ice, right, ice volume will be more than water volume. So water will expand and transforms into ice. Okay, so this is known as anomalous expansion of water. This is called anomalous expansion of water. dP by dt in that case, that is here what is happening, final volume of the liquid is less than the initial volume of the solid. Vf is less than Vi. Vf is less than Vi. When Vf is less than Vi, dP by dt equal to Clausius-Clapeyron's latent heat equation, dP by dt equal to Vf minus Vi, L by T into Vf minus Vi. Vf is less than Vi means this term becomes negative, entire dP by dt term becomes negative. Okay, dP by dt is negative implies what? When you increase pressure on the substance at melting point, its melting point decreases. When you decrease pressure, melting point increases. Okay, decreasing pressure means this effect will be with opposite side. Okay, what are the examples? Ice we can give. Okay, bismuth, gallium, etc. Okay, gallium. Temperature, when you increase pressure on gallium, right, what you call, when you transform gallium from solid to liquid, its what you call volume will decrease. Okay, means solid gallium's volume is more than liquid volume's gallium. Gallium's volume. Okay, similarly bismuth is another one. Bismuth is another metal. Best example is ice only, water. Okay, right, these three can be given as popular examples for this process. dP by dt is equal to negative. Here what is happening, right, when you increase pressure on the substance, its melting point will decrease. Okay, this concept is used in, this is anomalous expansion of water we say. That's why we are not supposed to, in a refrigerator, if you observe, we are not supposed to fill a glass bottle completely with water up to the brim, and we should not put it in the deep refrigerator. Okay, when you try to put it in the deep freezer, what will happen, right? Whenever water becomes frozen into ice, volume of ice will be more than the volume of water, so ice tries to expand. Okay, breaking the glass bottles. That's why in all cool drink bottles, if you see, they won't fill, just like in Kinley water bottle or water bottle, water is filled up to the brim. Okay, you'll get full water bottle. But when you take a cool drink, okay, and it's a glass bottle, they'll leave some space out. By chance, if somebody freezes that liquid by putting in a refrigerator, also the liquid will expand on solidification, the bottle should not break. Okay, that's why always they leave out some gap. Okay, they'll calculate what will be the volume of that solid phase of that liquid, Coke or whatever it is. Okay, right, they'll leave that space extra for safety. By chance, if somebody knowingly or unknowingly puts in the deep freezer, right, if it gets solid, the ice should not break. Even if you take a metal bottle, right, copper bottles nowadays, steel bottles are coming, right, you fill it completely with water and put it inside the refrigerator and see it next day. When it becomes ice, right, the bottle will get, even though it's a metal, the bottle sometimes, if it is an attached bottom, it will break. If it is not an attached bottom, the bottle gets deformed totally. Okay, that is expansion power, what you call, that is power of expansion of ice. In cold countries, In cold countries, what happens is water pipes and sewerage pipes, the temperature goes to -5, -10 degrees Celsius. Okay, whatever is in liquid form, when it expands, what you call, right, liquid expands, water expands, becomes, when it becomes ice, and these drainage pipes or what you call water pipes will get broken. So they leave that complete space there. Okay, enough, what you call, enough space to allow the expansion, such that the pipeline will not get broken. Okay, and also increasing pressure will decrease melting point is used in ice skating, etc. You must have seen some European countries, what's called, people doing what's called ice skiing. What happens, right? Ice, suppose that the temperature is in that country, temperature at that time is -5 degrees Celsius. In -5 degrees Celsius, right, water will be in the form of ice. Okay, they'll take ice platform. Okay, right, now if they increase pressure, the temperature is at -5 degrees Celsius, water will be obviously in ice form. Now they want it to convert it into liquid form. They cannot raise the temperature of the entire substance, isn't it? So what do? They'll increase pressure on ice. When they increase pressure on ice like this, okay, what will happen? Wherever pressure increases, melting point decreases. What happens is melting point of ice decreases. Instead of melting at 0 degrees Celsius, now because of that increased pressure, ice melts at -5 degrees Celsius only. Okay, -5 is less than 0 degrees Celsius, isn't it? So ice melts at -5 degrees Celsius. There the atmosphere is at -5 degrees Celsius, means wherever the point of pressure, whichever point the pressure is increasing, at that point, right, ice transforms into water, and that water will act as a lubricant for the person to move smoothly. Okay, it is like a lubricant, okay, acting as a lubricant so that he can move freely. And how to increase pressure means, suppose say we are standing here like this. Okay, I'm standing here like this. Okay, so what is pressure, right? What is nothing but, pressure is nothing but force per unit area, F by A. Force is nothing but, right, my weight only. My weight is the pressure, force per unit area. Okay, my weight mg by, what is area? Area of both my feet will become the area. Okay, now I want that pressure should be so high that melting point of ice should decrease from 0 degrees Celsius to -5 degrees Celsius, means the pressure should be very high. How to increase? This much pressure is not sufficient. Then how to increase pressure? I cannot raise my weight from say 70 kg to 100 kg, no, for the dancing, isn't it? So the next thing is to reduce area. Okay, how to reduce area? I cannot shape my legs to knife edge shape. So what do people do is, they wear knife edge shaped shoes. They'll wear knife edge shaped shoe like this, and they'll be standing on that shoe, such that the area of contact, cross-section area, is extremely small. When area is small, right, say 20 times less, pressure will be 20 times more. Okay, that high pressure, wherever that knife edge shaped shoe touches the ice, at that point melting point of ice will become -5 degrees Celsius, atmosphere will be at -5 degrees Celsius. So what happens there? Wherever he's putting his feet, right, ice keeps on melting and becoming water. That water will act like a lubricant, and the person, when he moves off from that place, again the pressure becomes normal, right? Melting point will again go back to 0 degrees Celsius. Their temperature is -5, so it becomes ice only. So wherever they are putting their feet, right, there it becomes ice, water, and when they remove their feet immediately, again pressure will be less, melting point of water goes back to 0 degrees Celsius. Okay, so these are some practical applications of Clausius-Clapeyron's latent equation. Remember, it is applicable only for first order phase changes. This question has come in GATE and many exams like previously. Okay, what are first order phase changes? Phase changes, phase change which requires some heat for the phase change to occur, are known as first order phase changes. Okay, they are all isothermal isobaric process. Keep these important points in mind, right? This will become your preparation for any exam you are appearing, right? Thank you.